Yeah, a couple of answers. So the problem set 9 is due on Tuesday. Unfortunately, I have one of my dental emergencies I have to deal with tomorrow, so I'm not sure whether, well, I won't be here for the problem session tomorrow. But whether I can get one of the TAs to do it, or whether we'll do it on Zoom, I'll let you guys know, all right? All right, very good. So, we've been talking about classical versus non-classical light. And I think we saw in the last lecture how subtle this can be. And, the questions of how we, what kinds of differences there are between what we were say single photon states versus coherent states and the kind of phenomena we see. And we've seen different aspects of this so far. We've seen, the question of photon statistics as being one of the ways in which we characterize what we call classical light versus non-classical light, in the sense that we see when we do detection of electromagnetic waves, the energy is absorbed in discrete chunks, but that can be completely described by the properties of the way the matter interacts with the field, and the statistics of that are just random counting statistics, and that doesn't really say much about the fact that there are photons as a particle. But in particular, what we saw is that the fact that when we have classical light, meaning the state itself is a statistical mixture of some multimode coherent state, that if we have such a case, then the photon statistics tells us that the fluctuations in the photon number are always greater than or equal to the mean photon number. That is to say, if the statistics are generally super Poissonian, where there is one part of the fluctuations we say that we think about as coming from the fact there's a discrete counting and those fluctuations, and then additional fluctuations that can arrive from the fact that we have an unknown coherent state. We have fluctuations in the amplitude, fluctuations in intensity. So that's one of the ways in which we have learned about classical versus non-classical. If we violate this, we would say that state of light is non-classical. But that's not the only signature. And what we saw in last lecture, we talked about photon counting correlations. Where we sent some source onto two photodetectors, and we looked for coincidence. And the nature of these correlations between photon counting looked quite different, depending upon whether the source was coherent state versus a single photon state. So correlations in the counting, or if we want to think about them, higher moments of the distribution are telling us something important. And as I mentioned, the particular experiment that we discussed last lecture relating to the heralded single photons, that experiment was done in 1986. Okay, but this question of photon statistics and photon correlations and the relationship between classical and non-classical light goes way back 30 years before. And one of the most important examples, and that sort of led to the whole story of quantum optics, was the Hanbury-Brown and Twiss experiment, which was in 1956. Okay. Now, it took me a long time to learn that Hanbury, Brown, and Twiss are actually two people. Hanbury Brown is one person, Twiss is another.
It sounds like a cocktail name.
Sounds delicious.
Yeah, right? Sounds like a good drink, man.
Yeah. So to lead up to this a little bit, and the controversy that this stirred, and that it took basically almost a decade for people to understand what the heck was going on with this from a quantum perspective, was solved by the great Roy Glauber, who won the Nobel Prize in 2005 for quantum optics. And Glauber's notes that are kind of tell the whole story is one of the best pieces of physics writing I've ever read. I'll put it on the web soon, and I highly encourage you to do it, to read it. So let me tell the story a little bit and think about why this was a controversy and how we understand it now and how it gave us the foundations of quantum optics. Okay, so to do that, I want to first back up a little bit and go back to think about what we call classical light, which is to say we have some field, let's say the complex amplitude of the electric field, which we think about as a random variable. So this is the story of classical statistical optics. Now, we've been talking about this for the last week or so, and we talked about a particular model, example of this, where we thought about thermal light. Sometimes known as chaotic light, where we wrote this complex amplitude as associated with a set of independently radiating dipole radiators with random phases, right? And what we showed, if we had those N oscillators, is that we wrote it as some E0 alpha at T, e to the minus I some omega T, okay? Where this was a classical random variable. It's the complex amplitude that's a random variable, okay? And this came from the idea what we described some few lectures ago, where we said, well, there's some particular radiator as a function of time. The electric field oscillates, and then there's some jump in the oscillation. Oops. And then there's some other jump, and then it goes on for a while, et cetera, where there's punctuated with random phases, okay? And we had a probability distribution associated with this complex amplitude that was Gaussian. And I can think about that in terms of the mean, thought about that in terms of the mean photon number, right? It's something we've discussed, okay? So this is one aspect of the field, that there's a random amplitude. There were intensity fluctuations in this problem, right? When we looked at the intensity of the field, what we saw was that we had these kinds of fluctuations in the system, right? Where the intensity was the square of the amplitude. So these are functions of this particular expectation value related to the intensity is looking at the amplitude squared to some power. And we calculate that expectation value based on this probability distribution. So this is one aspect of the field. How is the amplitude fluctuating? More than the amplitude, the square of the amplitude, the intensity. But another thing of interest, often, if we're going to analyze this source, is something more about the nature of these collisions. When do they occur? How often do they occur? In some statistical manner. And to some degree, over what length of time scale do we see that the field has a well-defined phase, and thus we would expect to see interference of the wave with itself in an interferometer over some time scale, after which time, if I have too much separation, I would lose coherence. That's sometimes called the coherence time, okay? So how would you measure the coherence? And the coherence time thus tells me something about the nature, how often these collisions happen. So that's a measure of, the nature of this field. It's something we might want to study. So, the question would be, how would you measure the coherence? I'll call it the temporal coherence time. How might you measure that? What? A holodyne measurement is I need a local oscillator here, and so we're on the right track. Yeah.
Maybe we have this source.
Yeah.
And we create two parts.
Yeah.
One is a bit of time shifted.
Yeah.
It proposes a bit more optical part.
Yeah.
And then I connect them to.
Perfect. That's called an interferometer. It's exactly what you would do. So what we would do, as Amar suggested, is I would send this light source onto a beam splitter and divide it into two paths. Let's draw those two paths over here. And I can say move this mirror by some amount. And then I recombine these two paths on a beam splitter. And let's just look at one of the output ports, okay? And so there's some, I'm gonna forget about the vector nature of the field. I mean, I have to, it's got some amplitude, but I square that in vector. So I'll just think about, there's some, at this input port, there's some electric field at this input time, and it travels on these two paths. These two paths are associated with, have some length, I'll call them L1 and L2. And so what I see over here is the superposition of the two electric fields, as we've looked at, you know, early in the semester, dealing with all the beam splitters and all here. So this, I'll call this the input field. The output field at some time is equal to the superposition of the input field at the retarded time, T1, plus the input field at the retarded time, T2, where the retarded time is just how long back in the past the light traveled, right? This is how much time it takes light to get from this port to that port along these two paths. Is that clear? Okay. So what an interferometer does, this kind of interferometer does, is what's called the temporal. It looks at the temporal correlations. How does the electric field correlate with itself at two different times, because it goes along two different paths in this case, and we're looking at that interference. So what we would measure at the end is the intensity. Okay? So the intensity at the output port is the time average of the square of the amplitude. That's what a square law detector measures, depending on how long. I want to do this for as long as possible, okay? So that's what I'm measuring, and from that I want to deduce this correlation length. Now, what I'm really interested in, though, is something about the statistics, which is about, I don't know what the field is at any given time, I just know the probability distribution. However, if the source has certain statistical properties, we can relate the time average to the statistical average. So this guy will be equal to the integral over the probability distribution, but I'll just loosely write like this. So this is a time average, and this is what we sometimes call the ensemble average, or the statistical average. And the question is, under what conditions will these two be equal? That depends on the nature of the fluctuations, but if they are equal, we say the statistics are ergodic. Which is to say, as a function of time, the electric field is fluctuating. But what that is at any time is sampled by this probability distribution. So what I see at different times is as if I took a random sample from the probability distribution according to whatever P of probability is. So chaotic light has that property. It's ergodic. I can equally well average over time, and what I'm going to see is equal to, for long times, the ensemble average. The term ergodic is really a term that comes more from classical mechanics. The idea is that a particle moves over all possible places in phase space in a kind of uniform way, so I could just sample from over time. The trajectory is if I've sampled over the probability distribution. So that's one property that that is true of this kind of source, okay? The other property that we're gonna, okay, but before I do that, let's just write this out then. So so this is my ensemble average. So let's look at this particular electric field that's coming from the interference in this case. The output intensity thus is equal to the square of the amplitude, which is 1/4 the square of the first term plus the square of the second term plus the cross term, which is twice the real part of the ensemble average of the product of these guys. I'm sorry, this is not correct. This is the input. Everyone agree with that? So I'll put the 1/4 out front. Plus, yeah. So I just squared that amplitude. Yeah.
So can I think of that third term as essentially the beat note between the two arms of the...
Yeah, I mean, a beat note is a little bit restricted to thinking about two monochromatic fields, right? But you're right, that would give to a beat note if they're two monochromatic fields. What I would say is this is the autocorrelation function. I'm correlating the field with itself, that's auto, but at two different times, okay? And that's exactly what we wanted, right? The idea was that we wanted to see if I separated these fields by two different times, are they well correlated with one another? If they have a well-defined phase relation, they'll be well correlated, but at some point, they'll lose that correlation, okay? So that's what this thing does. And so now we can, there's one other feature that we're going to use about this kind of chaotic light, which is that it has what are called stationary statistics. So both ergodic and stationary. What we mean by stationary, in this case, is not nice paper, is that the statistics are not changing with time. That is to say, it doesn't matter whether I'm looking here in time or here in time, the nature of the fluctuations are not changing with time. It's not saying that nothing changes with time. It's saying that the statistics don't change with time. The probability distribution doesn't change with time, which is to say that anything I measure doesn't depend on the origin of time, but only the time difference, okay? So since that's true, this thing, the intensity at this time is the same thing as intensity at the initial time. So this is equal to, because it does, I can shift the origin of time, and that's the same thing.
So is this a condition we're imposing?
It's a condition that we're saying is true for chaotic light. I'm not just assuming it to be true, it's provable true, but I'm not proving it to you, okay? So if the statistics are stationary, then it doesn't depend on the origin of time, and I can shift the origin of time anywhere I like, and I'll get the same because basically what the origin in here doesn't affect this, okay? And so this is the same thing again. And this thing only depends on the time difference. So I shifted everything by this amount, that became, or T2 minus T1, E in at 0. So by shifting the origin of time, what I find is what I see The intensity at any time is the same. The input intensity is not changing with the function of time. So this thing becomes 2 times the input intensity, which is 1/2 the input intensity. That's these 2 terms. And then I have plus the real part of E in T1 or T2 minus T1 star E in S0. All right?
Why do both of the first 2 terms go to 0 just from the shifting?
I can shift any way I like. I can shift this guy by this amount.
Yeah, like in
Each one is independently shiftable. I can shift the arcing any way I like if this thing is stationary.
Is another way of saying that is you're saying that the input signal is time invariant?
Well, I'm not saying the signal is time invariant. I'm saying the moments of the distribution. Things are fluctuating all over in time. But the mean and variance and kurtosis at every moment is the same. And it doesn't matter when I look, I'll see the same fluctuations and every moment of the distribution.
But this is because of the type of light that I'm setting it.
That's right. If I had one pulse,
And it's
then
different.
it wouldn't be,
Yeah, exactly.
it wouldn't be stationary.
Yeah.
Right.
Right.
Yeah, absolutely. Good. Okay, so I have what I expect. Firstly, if I have a balanced interferometer, if T1 equals T2, then this is also the intensity. And then what I get is that all of the intensity comes out the output port that went in. That's if I have a balanced interferometer, then all of the intensity goes. I have constructive interference. But whether I get constructive interference or destructive interference will be determined by this correlation function, okay? So this correlation function, let's go to the next board. I'll call G1 of tau, which is the first order correlation function in statistical optics, is E1 or E, in this case, input tilde at tau star correlated with E in at 0. Okay? G1 at 0 is the intensity. Okay? Now, our complex amplitudes over there, we express them in this way. So this is equal to E0 squared e to the I omega tau times the correlation of the complex amplitude with itself at 2 different times. Okay? Now, I sometimes give this problem for homework. It's kind of annoying. You guys are spared. I'm just going to give you the answer. All right. The answer is that for this kind of source with these random phases, this thing is equal to the following. It's equal to the number of oscillators times e to the minus t over something I'll call tau c. Okay? Yes, Don.
Why do you call it G?
G is what it's called.
Okay.
Glauber called it G, someone else called it G, but he didn't call it G for Glauber.
Okay, so
This is what we call it. This is called G1. I don't know why they would call that. Okay, but so when t is 0, this is what we expect, right? This is what we said. But when t is not 0, the correlation function falls off exponentially, okay? And the rate at which it falls off is what we call the coherence time. Why is it called the coherence time? Well, let's plug this in, okay? This comes from, you can do this from the kinetic theory of gases and statistical physics, and that's what people do. Okay, so let's just plug that in now to this expression for the output intensity at the interferometer. What we find is that it's equal to 1/2 the input intensity plus N0 e squared times cosine omega tau, that's the real part of this, e to the minus tau over tau c, where tau is equal to L2 minus L1 over c. It's the difference in path length between the two arms of the interferometer in time units, okay? So, this, of course, is equal to the input intensity. So this whole thing is equal to the input intensity over 2 times 1 plus cosine omega tau e to the minus tau over tau c. Okay, so let's sketch this. What do we see as the intensity on this output port of the interferometer as a function of the path length difference, or as a function of equivalently the time difference between those two paths? What does it look like? Right, so I have, at this point I have, if my tau is this, okay? Tau is the path length difference in time units. So here is my output intensity as a function of tau. Here's the input intensity. When tau is 0, all of the intensity comes out of that. But as tau increases, as the path length difference increases, I see these damped oscillations. And when the damping gets to be infinity, it asymptotes to half the intensity, right? And so this is what I was trying to draw. This is I over 2, and it looks like so this is what I would see on, these are the interference fringes I would see. When tau is much, and this has some, characteristic time scale of decay, which is the coherence time of the oscillator. When the path length difference is small enough that tau is small compared to tau c, I see interference. But when tau becomes large compared to tau c, half of the intensity goes out this port, and what happens to the other part of the intensity? It all goes out that port. So it's just, at that point, there is no interference. It's just as if there are two possible alternatives in either this port or that port. The only time you would expect all of the intensity to go here or all of the intensity to go there is if you have constructive or destructive interference. But when tau, and thus the path length difference, is sufficiently long compared to the coherence length, or equivalently the coherence time, I don't see interference anymore. So this is a way of measuring, this is how you would measure the coherence time. You would look for the visibility of these fringes, which is how different is the brightest point compared to the darkest point. And as it decays, the visibility, you'd say, okay, that's the time scale over which, and that tells me the coherence length or the coherence time of my source. Okay? Fine, that's classical optics, and that's classical statistical optics for these typical kind of statistics. Now, Hanbury, Brown, and Twist were actually astronomers in Australia. I don't know if they were in the outback or where the heck they were, but they were wanting to measure, not in their case, originally they were trying to measure not coherence times, but coherence areas. They wanted to know whether two sources in the sky, 2 points in the sky were coherent, or were the points, 2 different points in one star, or were they 2 independent stars? And they wanted to measure that. And to do that, they needed this big armed interferometer that was very hard to stabilize. And so they thought, so they were thinking about spatial coherence, but this is what we call temporal coherence, which is 2 different points in time. And I want to, what they thought about is, well, wouldn't it be nice if instead of trying to have this interferometer that's hard to stabilize and is sensitive to vibrations, if I just can forget about that and instead just correlate, instead of the field with itself, which is what we're doing in this kind of Mach-Zehnder interferometer, let's just correlate the fluctuating intensity with itself. So they said, hey, I'm just gonna do this kind of experiment, the kind we looked at just a moment ago, or last lecture, whatever that moment is. I'm gonna send in a source, I'm gonna have 2 detectors, and then I'm gonna have some time delay. So these are 2 square law detectors, and I'm just gonna multiply them together and look at the time average. So I have an intensity here, I'll call this the intensity at 0 and the intensity at tau, and then I'm gonna look at the average of the intensity with itself at 2 different times, okay? Or equivalently, that, okay? Which we call G2 of tau, okay? And so this is an autocorrelation of the intensity with itself at 2 different times, as opposed to a correlation of the electric field with itself at 2 different times in that G1 correlation. Yes?
Why did they put the delay line after the detector before they mixed the readouts? Could have you put the delay line before the detector and then mixed out and got the
Yeah, either way.
Okay, yeah. Thank you.
Okay, yes?
Is there a G0?
No. It starts at 1.
Is there a G6?
Yeah, there is. We'll talk about it. Okay, so, all right, now they were radio astronomers, or astronomers, but they knew about random signals, okay? And from their point of view, they were thinking about this from the point of view of statistical optics, not from the point of view of quantum mechanics, okay? And they knew that, when we had, these guys are described by this Gaussian distribution. Okay? That's the probability distribution that describes these complex amplitudes. It's a Gaussian with 0 mean in this case. Now, those who know statistics well know that a Gaussian distribution is only determined by its means and its covariances. There's nothing, any other moment, it's a 3rd order moment, a 4th order moment, a 6th order moment, is some function of the means and covariances, because that's the only thing that defines the Gaussian. And by a version of what's called a Wick's theorem, okay, so if I have a multivariate Gaussian, so I have some probability distribution of, let's say, 4 variables. And I look at some moment that's associated with those variables. I want to look at that expectation value. And let's say that this is a multivariate Gaussian with 0 mean. That means the mean of x1 and x2 and x3 and x4 are all 0. okay? They have some, that this expectation value is equal to x1, x2 times x3, x4 plus x1, x3 with x2, x4 plus x1 with x4, x2 with x3. Did I miss any? I think that's every one of them. I look at all pairs. That's a form of Wick's theorem. There's another name for it that I can't remember that's specific for Gaussians, but this is just a property of Gaussians. Again, sometimes I do this for homework, you guys are on the hook. Okay. So that, in this case, I can do this. I can think about this in terms of the variables. This and its complex conjugate. Right? This equals that. And because of these guys and the way the phases work, the only things that are non-zero are the things of something with this complex conjugate. Otherwise, the phase is zero. So there's two terms here that contribute to Wick's theorem. This with this. And then okay. So those, by Wick's theorem, this moment, this 4-point correlation function, factorizes into the sum of these two products of 2-point correlation functions. But what are these things? That tells me that the intensity correlation function, by stationarity, this is the same as this. Plus the absolute value of that squared, which is G1 squared magnitude, which is the thing we wanted to measure, right? So by measuring this intensity correlation, I can measure the field-field correlation, which is what I needed in order to get that. And this itself, so let's just call this is I in squared, and this is I, according to what we had over there, the magnitude of that thing up there is going to be equal to I in squared e to the minus 2 tau over tau c. Yeah. So this, I think the whole thing should have had a factor of 2 in it, but I don't really care about that. What I'm really, the point here is that this is equal to this. And so by doing this, in principle, I can measure the coherence time without an interferometer, just by looking at the fluctuating intensities with one another and correlating intensity with one another and seeing how that would fall off. And so if you looked at that as a function, it would look like this. There's actually no factor of 2. It's actually correct. It just is that envelope function. It's the square of that envelope function. When, notice, and pay close attention to this expression over here, we're looking at the correlation of the intensity with itself. When the time difference is big compared to the coherence time, the intensities are statistically independent, which is to say the average of the product is just the product of the averages. But when we're right on top of one another, then we see this effect of the enhanced intensity fluctuations, because if we looked at I0 when tau is 0, what we just said over here, where we had this n factorial business, this is equal to 2in, right? Because that's what we said the statistics were. So when I'm right, when the tau is 0, I'm looking at the expectation value of I squared, and the expectation of I squared is twice the expectation of I squared. And when the tau is big and they're statistically independent, it's just I squared with no 2. And that's kind of what we expected. All right, that's nice. So what's the problem? Why is this a paradox at all? Well, this drove people crazy for the following because of quantum mechanics and what Paul Dirac said in 1927, 8, 9, something like that. 19. Which is, okay, I can equally well understand the classical experiment in terms of photons. But in this experiment, each photon interferes with itself. That is to say, I can think about whether I see a click here or here as it being associated with a probability amplitude rather than an electric field. And there's a probability amplitude for it to go this way, there's a probability amplitude to go that way, and those amplitudes then superpose, and I can calculate the probability amplitude, and thus the probability as the square of the amplitude, photon by photon. So the reason the photons go one way or the other is not a collective effect. This was somewhat debated in the early days, and Paul Dirac said, beware, each photon only interferes only with itself. The 2 photons don't interfere with one another, okay? And this was dogma as we understood it. So the question is here, how do I understand this in terms of interference of the photons? Because what I'm correlating is not a photon appearing here or here. There are 2 photons that are associated with seeing this product, because I'm seeing intensity here and here, which means I had to have seen a click here and here, separated at these 2 times. And Dirac told us that no 2 photons interfere with each other. A photon only interferes with itself. And that drove people crazy. They said this effect can't be true because it doesn't agree with quantum mechanics. Okay? Because this is not an experiment that looks like that. So Glauber said, no. To really do this, we need to now show how to understand this effect quantum mechanically. Okay? And which is where this story of quantum optics really began. And to do that, the point is now we want to think about going beyond our semi-classical description of photodetection. We wrote down a semi-classical description of photodetection whereby we treated the matter quantumly and we treated the field classically. Now let's do the same thing where we treat the field quantumly as well as the matter. Yes?
So if we, if we didn't, would we expect that if photons didn't interact with each other, that it would be flat? The I squared would just be 1?
Yeah, I mean, this seems like, I mean, this is interference. Interference of the waves at the quantum level is interference of the probability amplitudes. So we would, this experiment should in some sense involve interference of probability amplitudes. Now we're going to come to submit, I mean, I'll just say one thing about the punchline. The problem with the Dirac statement is true if at the end we're only detecting one photon. Then the path that associated with detecting that one photon are associated with, well, the photon could have gone that way, or it could have gone that way, or any other way, and the photon only interferes with itself. But what we more generally understand now, and the way we should think about it, is we can have multi-particle interference. What interferes are the histories of those multi-particles. This is an example of two-photon interference, and it doesn't in any way contradict Dirac, because Dirac was only talking about the experiments where I detect a photon or I don't, not correlating multiple photons. If I have experiments that are associated with the correlations between photons, we will see, maybe probably on Tuesday, that this is an example of two-photon interference. Yeah?
So the histories interfere with each other. Is that the same as, say, the paths?
Yeah, I think the question, it's a little bit more general. If there is one particle, then its history is its path. But here, let's do a little precursor. What are two possible histories that could lead to two photons, one going here and one going here? Well, there's two possibilities. I have these two photons. One of them is going to end up here and one of them is going to end up here. What are two possible histories that can lead to that? Exactly. Either this guy goes this way and this guy goes that way, or this guy goes this way and that guy goes that way. There is a probability amplitude associated with each of those histories, and we add those amplitudes together to get the total amplitude associated with this simultaneous go click and square. And that interference is this. And that is really the resolution. That's not exactly what happened in history, but if you read Glauber's notes, which you will, you'll see it. Yeah.
And that's regardless of what type of beam splitter I use, whether I use a 90-10, 50-50.
Yeah, I mean, there's some chance, right? It doesn't have to be a 50-50. Of course, we would weight the histories differently,
yes,
right? By those amplitudes for reflection and transmission. But there are two indistinguishable histories. If there's nothing in the universe that has a record of whether the white thing happened versus the yellow thing happened, then what we must do is add the probability amplitudes for those two histories and then square the amplitude to get the probability. In the case of having only a single detector, those histories are always associated with a single photon. And in that case, the single photon interfered with itself. In this case, the two photons interfere with themselves.
Does the indistinguishability of the series relate to their optical path lengths? If they had different optical path lengths, would you say they're still the same?
No, you'd have to ask whether, you'd have to, so whether or not you see constructive or destructive interference, we have to think about, in the same way here, in some sense, the wave packet's not overlapping with itself at this point. So in some cases, the path lengths can make a difference, but the point I was really trying to emphasize is that we can lose coherence between the histories if there's something else in the universe that correlates with those histories. So if that's how we lose coherence, that's called decoherence, which we'll study in great deal detail next semester. Yeah.
Is what you just described coupling with the environment?
Yes. That's exactly that right. Yeah.
So this is for 2 photons. What if you had some other even number of photons? Like
Yeah, we could have, and that's why we could have a G4 or G6 or whatever. So let's get to it. All right, so the Glauber theory of photo detection. Now this is it gets really, I'm just going to outline the ideas because doing every step in detail is going to reveal what's really important. I want to get to the high level aspects of it rather than the real details. So, we're thinking about this as a model where we think about an atom being ionized, and that ionized electron is my photo ejected electron that triggers a photo avalanche diode to make it click. Okay, so that's our model. So we want to know about the probabilities of, so we imagine we have some ground state, we have some ionization level, there's lots of energy levels, and then, up here is the continuum, and my photoelectron is, and there's some excited state in the continuum with some density of states that, and my interaction Hamiltonian in the dipole approximation is minus d dot E, but now E has a hat on it. Okay? Before just D had a hat on it. We treated the E quantumly. Now this is at the position of the atom as a function of time in the interaction picture. We do the whole time-dependent perturbation theory, rigmarole and such, right? And D, in this case, in the rotating wave approximation, we have dg matrix element with the time dependence here, dotted into E plus, and then plus, or the other way around, GE, where I emit a photon, that operates as a function of time, all in the interaction picture. So we remember the positive and negative frequency components are associated with the annihilation operator. So in this case, I absorb a photon, and I go from the excited state to the ground state, or I have the creation operator, which is the emission of a photon and the lowering from the excited state to the ground state, right? So this guy was, the sum over all the modes, blah, blah, blah. So with my e to the epsilon, e to the I, k dot x, minus omega t, and then annihilation operator. Okay, that's the Heisenberg picture of that thing. Yeah.
just to clarify, is that E and G as a function of time altogether, or is it?
Yeah, this thing as a function of time is this. It's the free evolution of that projector.
And that one picks up the minus omega t.
And that will be resonant with that.
And that term picks up the minus omega t.
That one has either the minus I omega t, and so it's resonant, right? That's the rotating wave approximation. And, okay, so if we did the same Fermi's golden rule that we did before, but now the point is that the initial state here has also, we have to think not just about the atom, but the field, okay? So there's some initial state of the field, and there's some final state of the field. Quantum state of the field. And we have to take both of those into account when thinking about the rate of absorption for this guy. And so that's only related to the positive frequency component here. And so this thing is going to be proportional to, okay, this guy gives me the dipole matrix element here, but this is proportional to the amplitude squared associated with the final state I'll forget about the vector because too many indices to carry around. Okay. So when I take this matrix element, I'm going to have all the stuff associated with the atoms out front, but as far as the field is concerned, it's this. Okay. Now, when I'm interested, what I'm detecting in my detector is the electron. I don't care what the state of the field is afterwards. My measurement record doesn't store that. So what I'm really interested in this when I sum over all possible values of the final field. Okay, so I can rewrite this as this times its complex conjugate so that is everyone see that? I just wrote this times its complex conjugate, and when I did that, I turned E plus into E minus. Okay? Now, if this is the set of all possible fields, then this is a complete set. And I can bring it outside, and this thus is equal to the expected value of E plus at R, I'm sorry, E minus at R, E plus at R, where the expectation value is over the, maybe I'll write it explicitly. Okay. So my rate of absorption is proportional to the expectation value of this operator. The expected value of this quantum operator with respect to whatever the state of the field is. Now, it doesn't have to be a pure state. I could have had this be a mixed state. So I'm just generally going to write this as the expected value of what I'm going to call the intensity operator, where the intensity operator at this position is E minus times E plus. It's just like E star E, but now with hats on it. Okay, so there's a whole lot of rigmarole that just said that if I had a general quantum field instead of having complex amplitudes, E and E star, which is what we had before, we saw previously that the rate of absorption in the semi-classical model was proportional to the intensity, which was the square of the amplitude. In the quantum model, it's proportional to the expected value of the intensity operator. Okay? It's not a big change of this thing. And Glauber called this G1, and I can define G1 at R1, T1, and R2, T2 is defined to be this quantum correlation function. I'm autocorrelating this operator with this, and then taking the expectation value, okay? If I'm not worrying about the spatial positions, often we're looking at the time, and we just think about this, we often just are thinking about, we have some fixed positions, we're not worrying about position, we're doing temporal correlations in the same way we were doing before. Okay, that's just forgetting about that. And if I have ergodic and stationary statistics, then again, this only depends on the time difference. And this is sometimes called G2 of one, or G1 of one argument. Just like we had before, G2 of tau, that's the same thing. So there's no big difference if I'm thinking about a single photo counter that is looking for seeded by a photon that photoionizes an electron that causes a cascade and I get a click. All that's different here is that instead of the intensity, I have the expected value of the intensity operator. Now, in particular, suppose I have a coherence state. Suppose my state were a coherence state. A coherence state is an expectation value of the annihilation operator. And if I have a multi-mode coherence state, then it's an eigenstate of every annihilation operator. So a multi-mode coherence state is an eigenstate of E plus. Okay? So E plus, the positive frequency component acting on this guy, if you say it's some time, times the coherence state, which is specified by a complex amplitude, has as its eigenvalue the complex amplitude. That's just the generalization of A hat acting on alpha, giving me the complex amplitude back. Everyone clear on this? This is saying the eigenvalue now is replacing every A there by alpha, and that becomes a complex amplitude. So if I had a coherence state, what would this be? Well, if I take the conjugate of this, that would give me E star. For a coherence state, this thing is exactly the same as we had before. It's no different if I have a coherent state. And that's kind of what we expect if I have a coherent state. The semi-classical model is the same. I could just as well, the quantum fluctuations in the coherent state are irrelevant. It just looks like it was the classical field. And if I had a statistical mixture of coherent states, then this thing would just be the statistical mixture of all those guys. And so for classical light, this thing looks exactly the same. The fully quantum theory gives us back the semi-classical theory. And there's no difference in this in looking at the single photon or single photodetector experiments. They would not see, there's nothing I would see differently in a single photon count experiment that I could distinguish between classical light and non-classical light. So we need to go beyond this and generalize this now. So imagine that there are two atoms, one in one detector and one in another. And when we want to look at the probability of having two photoelectrons being ejected, because those two photoelectrons are going to then cascade in their two separate detectors and cause two different clicks in the two different detectors. And we want to write down what is the quantum mechanics associated with that. Okay? So we go through the same rigmarole that we did before, but now the Fermi's golden rule is more complicated. The Fermi's golden rule is associated not with something that is first order in here, because that only involves the absorption of one photon or the emission of one photon, the raising of one of the atoms or the lowering of one atom. We have two atoms, okay? So this gets more complicated. And so let me just sketch this and we'll then continue it next time. And everyone's in luck, the homework is going to be delayed because we're still not there to the last problem. So, you know, well, that's good because we need more time.
What do you want the Wikipedia proposals?
That's your
By the 24th, I believe.
no, that is on your assignment. It says it, all the dates, I don't have them in my head. The assignment tells you exactly when things are due. I just don't remember. I think the 18th is my recollection, but I don't have it. Well, I can take a look at it together right after class. So I'll just sketch one thing here to start. So when we think about the two photon case, or the case of two photoelectrons being ejected, what I want to think about, I have my unitary time evolution here in the interaction picture. I really should time order this. This is associated with a single absorption or emission. That's what that term is. And this is involved with two absorption. They can happen at two different times. And so when I do Fermi's golden rule, in this case, I have to go to second order. We typically don't do that when you think about time-dependent perturbation. You usually only go to first order, but this is a second order effect. But the bottom line is the thing that's associated with two absorptions will be proportional to the following. So this matrix element says I start in some initial state of the field, and through the whole rigmarole of what happens here, I have two terms. Either one photon was absorbed at time T1, at position R1, or T2, R2. And again, I don't measure the field, so I have to sum over all final states of the field. What I then find is that this is equal to, or proportional to, what's called the G2 correlation function. In this case, G2, R1, T1, R2, T2, and then the same thing again. Which is defined to be equal to the expected value of E minus R1 T1, E minus R2 T2, E plus R1 T1, E plus R2 T2. This is my G2 correlation function. Notice, if I had a coherent state again, this would return the product of the two intensities. But if I don't have a coherent state in the quantum case, this thing is a little bit odd. This is not the product of the intensities, because E plus and E minus don't commute with one another. This is what's known as we'll discuss this more on Tuesday. The normally ordered product of the two intensities. So in Hamburg, Brown, and Twiss, we correlated the intensity with itself. But the full quantum description of it is correlating the intensity operated in itself through normal order. And those dots mean, forget about the fact they don't commute, just write all the A daggers on the left, all the A daggers on the right. So the normally ordered value of n squared is equal to the normally ordered value of A dagger A times A dagger A, which is A dagger squared, A squared. And as we will see, this gives us the picture of two-photon interference. This will completely explain the Hamburg-Brown-Twiss experiment, but it will also allow us to see correlations and two-photon interference that is not explained classically. Okay? So this will be our final story on Tuesday of the Glauber theory of quantum optics. Yeah?
So is Tuesday's homework delayed?
Yeah.
Okay.
Yeah, we're not, we didn't get to it. Yeah.
For the normal order, you don't have to play that game of working through computations.
No. What's different about this, what these double dots mean is, forget about the fact they don't commute. It's just a notation. It's a way of saying this operator with the double dots is the one where you put all the A daggers on the left and all the A's on the right. That's what that double dot notation means. And photon detection in the Glauber theory says what I'm measuring are normally ordered products of intensities. Those normally ordered products of intensities correspond to photon counting, which is the quantum generalization of the intensity-intensity correlations. Yes, Tuesday's homework will be delayed. I'll send a message, an email to her. Yes, me.
So you quantized both matter and field?
Yeah.
But space is still the motive?
We never were we don't have a theory of quantum space-time. That's called quantum gravity, and we don't need to worry about it. Yeah. But we need to get out of here. I'll take other questions outside. Thank you, everybody.